Why does time stop at light speed? You've probably heard this before. Einstein said, "Nothing can go faster than light." And somewhere along the way, someone told you that if you could travel at light speed, time would freeze. Most people think this is just extreme slow motion, like a cosmic pause button. That belief is not a little wrong, fundamentally wrong. Here's what actually happens. A photon leaves a star 8 billion light-years away. It crosses galaxies. It threads through the void between superclusters. It survives for what we measure as 8 billion years. And for that photon, zero time passes. Not almost zero, not a tiny fraction, literally zero. The moment it left that star and the moment it hits your eye are the same moment for the photon. The entire journey, 8 billion years of travel, is a single instant. No duration, no waiting, no experience of crossing anything. The universe aged 8 billion years. The photon aged nothing. And this isn't poetry. This is measured physics. This is what the equations demand. This is what experiments confirm. You think you understand speed. You think you understand time. But the relationship between them is stranger than any sci-fi movie ever showed you. It completely reshapes how you think about motion, space, causality, even what it means to exist through time. Let's make this easier to picture. Take your phone. Yes, right now switch on the flashlight and aim it at the wall across your room. That's it. Now here's the detail most people never consider. The light from your phone reached that wall in roughly 10 nanoseconds. That's 1/10 billionth of a second. Before your finger had even fully lifted from the button, photons had already struck the wall, reflected off the paint, and traveled back into your eyes. From your perspective, it all felt instantaneous. But this is where the strange imbalance appears, the part that overturns our intuition. You did experience those 10 nanoseconds. Your heart kept beating. Blood continued to circulate. Electrical signals fired inside your brain. Time moved forward for you. For the photons, however, there was no passage of time at all. The trip from your phone to the wall and then into your eye wasn't merely brief, it had no duration whatsoever. Which leads to the unsettling question: how can something cross a distance if, from its own perspective, no time passes at all? This is exactly where intuition breaks down. You assume speed is straightforward, distance divided by time. Faster means you cover more distance in less time, and the ultimate speed would mean crossing space in almost no time. But that's the mistake. Light doesn't experience almost no time. Light experiences no time at all. And that distinction isn't a word game, it's the entire point. Look at what just happened. You and the photon began at the same place, your phone. You both ended at the same place, your eye. Yet you aged those 10 nanoseconds. The photon didn't age even a fraction of that. You moved forward through time. The photon didn't. Same starting point, same end point, completely different relationship with reality. Try it again. Turn the flashlight off, then switch it on. Watch the wall brighten in that immediate burst. That instant is billions of photons for which beginning and ending are effectively the same event, birth and arrival, collapsed into one moment. No middle phase. No during. No passage of time in between. They aren't just moving incredibly fast through time, they aren't moving through time at all. People often call light the fastest thing in the universe. But that phrase is more of a shortcut than an explanation. It makes it sound like light is simply outrunning everything else. What's actually happening is stranger. Light isn't winning a race through time, it has stepped out of the race entirely. And this is where things become even more unusual. What we're talking about isn't something unique to light alone. It points to something much deeper, something built into speed itself, into the connection between space and time. That simple flashlight example just revealed a tiny fracture in how we normally understand reality. Now, let's peer into it. All your life, speed has been explained to you in a very limited way, not intentionally misleading, just incomplete. From childhood, you're taught that speed is distance divided by time. Travel 60 miles in 1 hour, and that's 60 miles per hour, straightforward. But that's only the surface description, a convenient label. Underneath, something far more profound is happening. You're always moving at one constant speed, not merely through space, but through space-time itself. And that constant speed is the speed of light. Let me repeat that, because it sounds unbelievable at first. Even right now, sitting still and reading this, you are traveling at light speed. It sounds absurd, but stay with the idea. Space and time aren't separate arenas where events happen independently. They're woven together into a single structure, space-time. This was one of Einstein's most profound insights. Within this unified fabric, you always move with one fixed total speed, the speed of light. But here's the subtlety people often miss. That speed budget is divided between two directions, movement through space and movement through time. If you remain completely still in space, none of that budget is spent on spatial motion. All of it goes into motion through time. You surge forward through time at the maximum rate. Seconds pass, you age, Tuesday turns into Wednesday. But the moment you begin moving through space, even something simple like walking across the room, a portion of that budget gets reallocated. Some of your motion shifts away from time and into space. You're now using a tiny portion of that total motion for movement through space, which means slightly less of it is flowing through time. As a result, your personal clock slows down. Harsh, right? But don't expect to notice it. At walking speed, the difference is microscopic over an entire lifetime. It would amount to only billionths of a second. Still, it's real. It has been measured. There's no arguing with it. The universe keeps precise accounts. Speed up more, drive a car, board a plane. A larger share of your motion shifts into space, and correspondingly, less is left for time. Your clock slows further. The effect is still minuscule, still impossible to detect without ultra-precise atomic clocks, but the cosmic bookkeeping never makes mistakes. Now consider the extreme case. What happens if you spend your entire motion budget on space? If nothing at all remains for time? The answer is zero. And what speed would require using that entire spatial allocation? The speed of light. This is why time halts at light speed, not because photons possess some mystical property, but because of this fundamental accounting. The total budget is fixed. The balance sheet must hold. If all motion is directed through space at light speed, there's nothing left to move through time. Light doesn't bargain or redistribute. For a photon, the entire allowance is spent on spatial motion, every last fraction. Nothing remains for temporal passage. So no time elapses. Not slowed time, no time at all. Pause and think about the implication of that. Speed isn't about outrunning time. It's about exchanging with it. The quicker you move through space, the more your motion through time diminishes. Light is simply the limit case total motion through space, none through time. This isn't a matter of interpretation or perspective. It's built into the universe's accounting system. But hold on to that idea, because it leads to a chilling question. How did anyone ever figure this out? Who looked at a beam of light and realized it experiences no duration? Who first grasped that space and time draw from the same allowance? Surprisingly, it began with a teenager imagining the impossible. The year was 1895. A 16-year-old student in Germany sat bored in class, his mind wandering far beyond the lesson. His name was Albert Einstein, and he found himself fixated on a peculiar thought experiment. What would it be like to travel alongside a beam of light? It sounded like a simple curiosity, but it carried world-shattering implications. Einstein was already familiar with Maxwell's equations. James Clerk Maxwell had demonstrated that light is an electromagnetic wave, oscillating electric and magnetic fields propelling each other forward through space. Maxwell had even calculated its speed, roughly 186,000 miles per second. And here's the crucial part: that speed was constant, always the same. The mathematics insisted on it. But there's a deeper implication most people never hear about. Maxwell's equations didn't describe light's speed as being relative to anything. They just stated the speed itself, plain and direct. No reference point, no extra conditions, just a fixed constant. That detail was unsettling. Einstein started thinking about it deeply. He imagined something unusual. What if I could travel right next to a beam of light? At first glance, the answer seems obvious. If you move at the same speed as something else, it should look still beside you, like two cars moving side by side on a highway. You look over, and the other car doesn't seem to move. But light didn't behave like that. According to Maxwell's equations, light always moves at around 186,000 miles per second. That speed doesn't change. So even if you chased it at 185,999 miles per second, even if you could somehow reach light speed, the light would still move away from you at its full speed. It didn't make sense. Einstein sat with that conflict for years, turning it over in his mind again and again. 10 years passed like that. The contradiction stood there unresolved. On one side, the idea that a light beam should appear frozen if you could move alongside it, and on the other, the insistence from Maxwell's equations that light speed could never change under any circumstances. Both of these statements couldn't be true at once unless our basic understanding of speed itself was incomplete, and unless time, too, was behaving in a way no one had properly understood before. In 1905, Einstein finally introduced the framework that resolved this tension, the theory of special relativity. His conclusion was radical for its time. The speed of light remains identical for every observer, regardless of how fast they themselves are moving. This wasn't because light possessed some mystical or privileged nature, but because space and time themselves flex and adjust in order to preserve that constant. In other words, the universe enforces this rule at the deepest structural level. So, if you were somehow able to chase a beam of light, you wouldn't observe the light slowing down to match your speed. Instead, the consequences would fall on you. Your clock would tick more slowly relative to others, and distances along your direction of motion would begin to contract. Space and time would deform around your movement so that light's speed would remain unchanged. Light does not accommodate your motion, your reality reshapes itself around light. That was the profound realization hidden inside Einstein's youthful daydream. The universe does not prioritize your velocity, nor does it grant special status to your frame of reference. The only quantity it protects, absolutely, without negotiation or exception, is the speed of light. There are no refunds, no loopholes, no workarounds. Phenomena such as time dilation, length contraction, and even the relativity of simultaneity, all of these strange and counterintuitive effects exist for a single underlying purpose: to ensure that light's speed remains invariant for all observers. And when you reach light speed itself, that protective mechanism reaches its ultimate limit. Time doesn't merely slow, it ceases entirely, because that is the only state consistent with keeping the cosmic constant truly constant. Light always comes out on top, not because it holds some privileged or mystical status, but because it exposes the deeper rules that everything else in the universe is forced to obey. Now here's where things take a turn. Up to this point, it might sound like we're drifting into philosophy abstract thought experiments about chasing beams of light across empty space, but that's not what this is. This isn't speculation. This is practical physics. This is engineering. This is technology that gets tested and verified inside laboratories every single day. So how do we actually know that time slows down? What experiment shows that this isn't just mathematical wordplay? Picture the simplest clock you could possibly design. Imagine two mirrors, one placed on the floor, the other directly above it on the ceiling, with a single photon bouncing back and forth between them. Each time the photon strikes a mirror, the clock registers a tick. Tick, tick, tick. Clean, precise, beautifully simple. Now place that same clock inside a train, moving past you at enormous speed while you stand still on the platform observing it. Here's the subtle detail most people never think about. From your viewpoint on the platform, that photon inside the train is no longer traveling straight up and down between the mirrors. Because the train is moving sideways, the photon's path tilts. It travels upward and forward, then downward and forward, tracing out a diagonal, zigzag trajectory. And diagonal paths, as basic geometry tells us, are longer than perfectly vertical ones. So now the photon has to cover more distance between each tick of the clock. But the foundational rule still applies. The speed of light cannot change. The photon cannot move faster just to compensate for the extra distance, because the constant must remain constant. So what gives? Time does. Since the photon must travel a longer path at the same fixed speed, each tick of the clock takes more time to occur. From your stationary position on the platform, the moving train's clock appears to run slower. elegant, precise, and, most importantly, real. This isn't an illusion, and it isn't a trick of perception. It's a measurable consequence of how space-time itself behaves. The clock on the train truly records fewer ticks. It isn't just an observational illusion. Less time genuinely passes inside that moving system compared to what passes for you standing on the platform. And this is exactly where human intuition starts to break down. You might instinctively argue that the passenger on the train would look back at you and claim that your clock is the one running slow, and you would be absolutely correct. From their frame of reference, your time appears dilated. Both viewpoints are valid, both measurements are real, and yet neither represents some universal master clock, because such a thing doesn't exist. The universe keeps precise accounts, but each observer receives a different record of the transaction. Now follow the implication further. As the train increases its speed, the photon's path inside that mirror clock tilts more and more, stretching into a longer diagonal with every increase in velocity. The longer that path becomes, the more time must pass between each tick, since the photon still cannot exceed light speed. Push this idea to its extreme limit. Imagine the train reaching light speed itself. At that point, the photon's path would flatten completely, becoming horizontal, which mathematically corresponds to an infinite distance between ticks. And if the distance between ticks becomes infinite while the speed remains fixed, the clock doesn't merely slow, it stops altogether. Not slowed time, halted time. Temporal progression ceases. So far, the pattern is clear. Speed represents an exchange between motion through space and motion through time. The speed of light is enforced without exception. And even a simple photon bouncing between mirrors demonstrates that time itself must bend to preserve that constant. But thought experiments alone aren't enough. Where is the real-world verification? It's sitting in your pocket. Your phone can determine your position on Earth to within a few meters. Think about the precision of that. A handheld device locating you on the surface of a rotating planet that's hurtling through space at roughly 67,000 miles per hour, accurate to about the width of a car. How is that possible? Satellites, dozens of them, around 31, orbiting roughly 12,500 miles above you, each equipped with atomic clocks so precise they can measure time down to a billionth of a second. Your phone constantly receives signals from these satellites, compares the arrival times, calculates minuscule differences, and uses that timing data to triangulate your exact location. Elegant, practical, and entirely dependent on relativity being correct. But there's a detail people rarely mention. Those satellites aren't stationary. They move at about 8,700 miles per hour. According to special relativity, moving clocks tick more slowly. Because of that, satellite clocks fall behind Earth clocks by roughly 7 microseconds each day. 7 microseconds sounds insignificant until you remember that light travels at 186,000 miles per second. In that tiny slice of time, light moves more than a mile. Without correction, GPS positions would drift by miles daily. But there's another factor. Satellites orbit farther from Earth's gravity, and general relativity says clocks run faster in weaker gravitational fields. That effect adds about 45 microseconds per day. So you have two influences acting in opposite directions, one slowing the clocks, the others speeding them up, and they don't cancel. The net outcome is that satellite clocks run about 38 microseconds faster per day than clocks on Earth. The universe keeps precise accounts, so engineers compensate. Satellite clocks are pre-adjusted before launch, intentionally slowed so that once in orbit, relativity brings them into sync. This isn't philosophy, it's calibration. Open your Maps app and watch your location appear. That blue dot depends on relativistic corrections happening continuously. Every navigation request, every track delivery relies on time behaving differently at different speeds and gravitational strengths. Light speed being constant isn't theory, it's built into modern infrastructure. Now consider something beyond technology: particles that shouldn't even reach us. Cosmic rays strike Earth's atmosphere about 50 miles up, breaking into particle showers. One of those fragments is the muon, similar to an electron but heavier and unstable. A muon lives, on average, only 2.2 microseconds. Even near light speed, it should travel less than a mile before decaying. Yet, muons are created 50 miles above the ground. They should vanish long before reaching Earth's surface. But detectors measure thousands every minute. Even now, muons are passing through your body. This only makes sense if time dilation is real. At around 99.95% of light speed, their internal clocks slow dramatically. From our perspective, they live longer, long enough to reach the ground. From the muon's perspective, its lifespan is unchanged, but the distance contracts, the atmosphere shortens. Different explanations, same enforced constant. This isn't lab equipment compensating for relativity. It's nature demonstrating it directly. Billions of particles proving that time bends and duration warps at high speeds. So far, the evidence stacks up. Light clocks predict it, GPS systems rely on it, and muons confirm it at cosmic scales. But the deeper question remains: why? Why does motion through space reduce motion through time? What actually happens to light that removes duration entirely? Here's the unsettling part. Light doesn't experience time stopping because light doesn't experience anything. We say time freezes at light speed, and mathematically, that's correct. The equations give zero duration. Clocks halt. But that wording hides something deeper. For something to experience time stopping, it must experience time in the first place. There must be a before and an after, some sense of a frozen interval. Light has none. For a photon, emission and absorption are the same event, not separated by waiting, not connected by duration, but identical. From its perspective, that flashlight photon didn't travel to the wall and back. It was created and ended in the same instant. The trip didn't take zero time. The trip never existed. This isn't time slowing to a halt, it's duration losing meaning entirely. People say time freezes for light, but that implies light sits inside a frozen moment. That isn't accurate. Light has no moment to occupy. The ideas of before and after simply dissolve. You exist within time, you feel seconds passing, one moment leading to the next. Light exists outside that structure, not paused in time, absent from it. And the deeper realization isn't that light is special. It's that we are slow, massive beings bound to duration while light is free. And light's receipt reads zero, not small, not close to zero, but null. the category itself doesn't apply. This isn't physics being strange for the sake of it. This is physics pointing to the very edge of existence, the boundary where time has meaning and where it fades into something that only conscious observers perceive. Your phone flashlight shows you that boundary every day. Turn it on again. Do it right now. Watch the photons, leave the source, strike the wall, and return to your eyes. What you've just observed is something that feels impossible when you think about it closely. Billions of particles completing their entire lives with no passage of time, no sense of travel, no interval between beginning and end. Birth and termination collapsed into a single event, repeated across the space in front of you. You aged while reading this sentence. They didn't age at all. Every light bulb, every star, every screen you've ever looked at has been sending you streams of particles that have never experienced a single moment between emission and arrival. The universe keeps precise accounts, and now you understand how to read the ledger. Speed exchanges with time. Light allocates everything to motion through space, leaving nothing for duration. Time disappears, not metaphorically, but physically, measurably, and consistently across both natural phenomena and engineered systems. So the next time you see light, any light, remember what you're actually witnessing. You're looking at messengers arriving from across vast stretches of history while experiencing none of that history themselves. Photons released near the beginning of the universe are striking instruments today. Zero age. Immeasurable journey completed. So here's the question to sit with. If light experiences no time, does it experience anything at all? Is a photon better understood as an event rather than an object? And if existence requires duration, can we even say that light exists in the way we do? Leave your answer below. I'll see you in the next.